Hello and welcome to the seventh episode of the Data Science Daily Series. And I'm very excited to have you here. Today we are going to discuss about the data science development process. So far we have understood what is data science and what are the different subfields of data science. But actually, how do you go about implementing data science and bringing about the value that we have just talked about in the previous sessions? So today's video is understanding what is the end-to-end data science development process. And without further ado, let's get started. So let me share my screen. All right. So we'll talk about the data science lifecycle first and understand the different steps in the lifecycle. So this is also called the data science development process. We first start with the business problem understanding. This is very, very important, and we'll shortly discuss about why this is so important. Once the business problem has been understood, you then go on to the data collection phase. You collect data which is relevant to solve that business problem. And this can be from multiple sources or multiple departments in your organization. Once data has been collected, and we have to make sure that this is good quality, clean data. Data has to be pre-processed. That is the next step, right? You're doing pre-processing, you're removing outliers, you're doing, it's formatting and etc. to bring it into a format and into a particular quality level that you can use for further analysis. Then you start understanding the data and start uncovering the insights as you can see in the data. So you start visualizing the data, start looking at dicing the data in different ways and exploring it. This is called exploratory data analysis. Once you have explored the data, understood the data, you then move on to the modeling phase, which first starts with feature engineering. So don't worry, we will go over each of these in a lot of depth. We go over feature engineering, where you're designing features. We will discuss about what features are. Once features have been engineered, you go on to model training and evaluation. And model training and evaluation always go step by step. You're training a model, you're evaluating it side by side. You train another model, you again evaluate it, and so on. You do this keep iterative process until you arrive at a good model that you want to use and keep. Once you have arrived at a good model, you then go ahead for business report and approval, where you're showcasing this kind of a proof of concept to the business team, which is sponsoring the project most likely, and you're trying to get their approval and their feedback on how good your model is and how well can it gel into the real working environment that the business team is looking to use it in. After that, you go ahead to the model deployment phase, where you're deploying the model so that it can automatically take in the data, it can automatically build the models and churn out the results, right, over time. And more so if it is a real-time application. So what happens in real-time applications is you build a model where you have looked at a lot of historical data from the past, but if you have to do it in a real-time manner, you have to build the pipelines, right? So that data keeps coming in, it gets streamed, the model keeps running and inferring on top of the data and churning out results. So there is a model deployment phase as well, which is very, very important generally. And then you go on to model monitoring, where you're seeing whether the behavior of the model is as you would expect or not. All right. So this is in a nutshell what is the data science development process. Now, why is data science different from the regular software engineering approach? There are three paradigms that need to be considered. One is the data paradigm. The second one is the modeling paradigm, which is like a mathematical algorithm. And the third one is the code paradigm itself. So software engineering applications generally have the code paradigm, right? They're trying to build high quality code. But in data science, you not only have to build high quality code that solves the business problem, you also have to make sure that the data that you're working with is clean. So you're building a data pipeline. The modeling pipeline is also there, where you're building out good effective models, right, which are good statistical machine learning models which have been thoroughly evaluated on unseen data sets, right, so that they can generalize well into the future. So remember, this was the definition of machine learning. Machine learning is able to find patterns in the data, and it's also able to generalize on unseen data, right? So you have to make sure that the model that you're building is able to do that. So data scientists first start with understanding the business context, preparing the data, applying the right set of models, experimenting with the models to improve performance, right? Once they have experimented, validating the results with business experts, and finally deploying the model, right, with the CI/CD pipeline. And this will become more clear when we go on to the MLOps module, right? What do we mean by CI/CD? Don't worry about this at this point if you're not a software engineer. If you're a software engineer, you would probably be already aware of what is CI/CD. Okay, so let's start with what is the business problem understanding and what is this phase all about? Now, this phase is about understanding what is the business context of the problem. Why is the business team actually trying to solve this problem? Without a proper understanding of the business context, it is very dangerous to step into the analytical problem solving. For example, the business problem might ask you to predict a certain thing, or let's say forecast the sales into the future. And what you're actually doing is you're probably just analyzing the sales in the past, right? How it performed based on different levers. But that's not the business problem, right? If you build a dashboard looking at historical data and you just show it to the business, they will be saying, no, this is not what I want. I want a prediction, a forecast for the future, right? So you have to understand what kind of a problem it is. And remember, this goes back to our first session where we talked about the 4 stages of maturity for organizations, or 4 different kinds of analytics, right? There is the descriptive analytics, there's the diagnostic analytics, there's the predictive analytics, and then there is the prescriptive analytics. So you have to figure out where does the problem statement actually lie. And this brings us to the point that we need to convert the business problem to an analytical problem statement, right? What kind of an analytics is required? What kind of a modeling is required? And finally, bringing it one step further, are you solving a descriptive, predictive, prescriptive, or even a diagnostic problem statement? All right. Once you have understood the business problem well, you can go ahead to the data collection phase. And I can't stress enough why this is important, because data is the fuel that is fueling your algorithms. And if you're not able to source good quality data, it is very difficult that you will be able to build a model that satisfies the needs of the business team, or it satisfies the business problem statement itself. So data collection is very important, and data is very central. Why? As an example, Peter Norvig, the director of research at Google, said that Google does not have better algorithms, right? Google is very, very far ahead in their algorithms, in their research in AI in general, right? In their technology. And with respect to data science and with respect to AI, what they are developing, Peter Norvig mentioned that they have better algorithms, right? They're not working with some fancy cutting edge algorithms. Obviously, other people are also working with those similar algorithms, right? They don't have something, Google doesn't have something very, very, very different, right? Obviously, there will be some nuances, there will be some breakthroughs here and there, right? But as a general statement, we don't have better algorithms. We just have more high quality, structured, right? Well processed data, right? And data is very central. So in an organization, right, you need to think where your organization is, how much data mature it is. If it is data mature, or if you're trying to bring it to a data maturity level, right, that is the first important step before you can dive into data science. This is another graphic, right? Check it out. I made a fully automated data pipeline that collects and processes all the information we need. Is it a giant house of cards built from random scripts that will all completely collapse the moment any input does anything weird? It might not be. I guess that's something, whoops, just collapsed. Hang on, I can patch it. So this particular story is telling about a data pipeline has failed, right? You have so many scripts in so many different places and you're trying to process the data. Even if one data is not processed correctly, right? It's in a particular structured format, right? If you're talking about tabular data. If one column is not processed correctly, a few other columns that are based on that column will not get processed by the code, right? Because a code is just a logical sequence of operations that need to be performed, right? So data pipeline is very important. And in this step, actually, we are just talking about data collection. The next step will be about data pre-processing. So what is data pre-processing? Does your data have any missing values? If there are any missing values in your data, right? If you're missing data for any particular months, was there a reason why they are missing? Or, right? Or it is just that data was not collected at that time period. So there can be multiple things happening. Either the data can be all zeros, the actual value that happened in that time frame could be zero, and that's why it's not there, or the data itself was not collected. So you need to understand what is the rationale behind the missing values and accordingly fill the missing values, right? There are different ways of imputation. We call missing value, filling missing values, we call it missing value imputation, right? So how do you impute missing values? Also, the second problem could be you are working with so many different kind of data sets and they have different frequencies. So you have to figure out, does the data have the same frequency for all the variables in terms of the time component? Let's say there is no time component. Is it having the same granularity, right? Let's say each data set that you have, it is not at a product level. Some data sets are at a product level, right? Some data sets are at particular item levels that was sold, right, with the unique tag that they were sold. Some products are at a product category level, right? Some products are just at a big company level, right? Some data sets are at a big company level. So you need to make sure that your data is at the same granularity. Otherwise, you'll not be able to use it. You'll not be able to merge and use it. Finally, is the data present in more than one file, or it's all in one file already? So if it's not in one file, you need to merge it, you need to clean it up, right? You need to do a lot of operations. So that is the step of data pre-processing, right? Now let's understand what is exploratory data analysis. You have pre-processed your data, you have collected good quality data, you have understood the problem statement. Now, based on the problem statement, you're trying to explore the data and understand the relationships in the data better and build your business expertise along with exploring the data. Right? So EDA is a very important phase for data scientists in general. It helps them achieve multiple things, right? When anyone asks you why you're performing exploratory data analysis, it helps you understand the data, understand the business rationale that gets reflected within the data, right? The business team might be telling you that this is what happens in the actual world. But when you're looking at the data, you will be able to corroborate and actually verify that, this is what's happening. And you will be able to dig deep further into the understanding of the data. So that's one. The second thing is you can unveil relationships which might not make sense, right? And these could be anomalies that you have figured out in the data. And these might be good discussion points to discuss with the business, right? Are they outliers? Are they influential points, right? What kind of anomalies are you seeing and why did they happen? So with this nice understanding of the data and with this active discussion with the business teams, right, you can go ahead with the next steps. So firstly, what are the relationships and correlations between different variables in your data? Are there any outliers in your data? How do the distributions of the variables look like, right? Are there any visually observable data points that indicate further inquiry? A fancy term for saying, are there any anomalies or influential points? So all of this is in the realm of exploratory data analysis, and we are doing a backward looking analysis, a historical analysis. So this is kind of descriptive analytics at this point, right? We have covered descriptive analytics and part of diagnostic analytics as well, right? If this anomaly occurred, why did it occur? If this time series causes the other time series, is there a strong statistical relationship between the two of causation? Can we say that one time series causes the other? So you have to do statistical tests for that. So both mostly descriptive, and also diagnostic analytics get covered in exploratory data analysis. And after that, we move into the realm of feature engineering, right? And this is where predictive analytics comes into the picture. Mostly if the problem statement, right, we are talking about a general data science problem, and general data science problems always have a prediction component attached to them, right? So this workflow is based for that, right? You might be able to remove certain components based on the problem statement itself, but in general, this is the flow. So let's come to predictive analytics. Now, feature engineering is basically, what are features first? You are engineering features that make it very explicit for the model to understand, right, what are the hidden relationships in the data. For example, do you have two variables that need to be transformed together to create a new one? If you have revenue and cost as two different columns in your data, you can do revenue minus costs to get profits. And profit is another variable that might be useful for your modeling problem statement. So you need to engineer features that make business sense, that are not so easily obvious in the data, that you need to create separately so that the model is able to learn very easily. It doesn't have to figure out these relationships, right, which you already know that they exist. So feature engineering is very important. Does your data have a time component? You need to extract the seasonality then, right? If you have categorical variables, we'll talk more about this in depth, right? Just an overview. If you have data sets like having categorical variables, you need to make them numbers. How do you do that, right? Does the EDA, which is short form for exploratory data analysis, suggest any other transformations, right? If you're dealing with time series, should you take a lag of other time series, and so on. Then we come on, once we have feature engineered and understood the data, right, and build the entire data set with the engineered features as well. Now you're trying to build the model, right? You need to build a data science model to solve the business problem and tune the model, right? Tuning means you're tuning the hyperparameters of the model. We'll understand what the hyperparameters are, but they relate to the architecture of the algorithm itself, right? The algorithm or the model is learning from the data, but the overarching architecture of the model, that is what you can also tune so that the model is able to learn better from the data. Remember, you always should benchmark complex models against simpler ones. It's not always to go ahead and say that I use the most complex neural network, right? A transformer model for a simple small problem statement. It doesn't make sense. If your simple model is also performing as well, the complex model has certain downsides. There is a lot of computational cost. There is a lot of black box things that can happen within the model that you'll not be able to explain. So the explainability will be lower with complex models. So always benchmark complex against simpler models. Choose the right metrics to evaluate your model, right? How are you evaluating? That needs to be figured out at this step. Make sure, this is very important, make sure that your model is not exposed to the data that you will be evaluating it on. If you're evaluating it on 3 months of data, make sure that the model has not learned on that data. Otherwise, that's cheating, right? That's just cheating. And you have to make sure that if someone else is reporting the accuracy of a model to you, you have to make sure, did they keep that data completely unseen? Nothing was done on that data. No normalization, no outlier analysis, right? Nothing was done. It was completely treated as unseen, like future data. You don't know what's going to happen. Only then, if you test it, that's true model evaluation. And make sure the evaluation is robust by different methods, like one of them is cross-validation. We'll again cover this in a lot of detail later on. Once you build the model, remember we talked about business report and approval. Are your stakeholders or the business sponsors aligned with the relationships identified by the model? Does that make business sense overall, right? It might not need to make business sense because you're not trying to align with the business logic, right? You're trying to build a model that unveils what the actual business relationships are. But on an overall level, that needs to be some similarity, right? Your model, if right, can learn a lot of noise as well, right? If you're giving a lot of macroeconomic data and you're trying to do something with it, it might learn patterns, but those patterns might not make sense. So you have to benchmark and anchor the model to the business logic. Are they comfortable or confident going ahead with using the model or not, right? Does the model meet the minimum acceptance criteria? So these are kind of things you have to discuss and understand. Then you go on to the deployment phase, where you have to do a bunch of software engineering, standardization, code quality checks, right? So that you can deploy the model. Do you have a mechanism set up for monitoring and fixing bugs that may arise, right? When you're deploying it and when you're expecting it, let's say, for example, to be a backend for a real-time system, real-time predictive analytics. Do you have a mechanism for automatically monitoring and fixing bugs that might occur when you're sleeping, for example? Are the data pipeline, model building, evaluation pipelines set up for enabling monitoring, right? Can you completely monitor each part of your entire code or entire project that you have developed automatically? This ties into the previous comment. Does the deployed code follow the best coding practices, and so on? And finally, you have monitoring. Is your data or model drifting through time? It's becoming noisy, right? It's becoming accurate. It can happen, right? Your data can change. Your definitions can change in the data. Are there inherent relationships that are changing due to inherent or internal or external factors? This could happen. Like in COVID, all relationships suddenly changed, right? So you have to think about it. You have to keep monitoring. You can't make decisions on a model that was built pre-COVID era, and you're using that in the COVID and post-COVID era. It might not hold, right? So you need to monitor the model's performance and the relationships as well over time. This is very, very important. And this is the field of machine learning operations, right? Model deployment, model monitoring. field of machine learning operations, which we'll again cover in a lot of depth later on, right? What is the evaluation criteria for refreshing the models and so on. Okay, so with this, we have covered the high levels of the data science development process. And we have covered how do you on a high level go about taking the data in, processing it, building the models, communicating the results, that is very important, right? And finally deploying it in a very nice software centric manner that people are able to use it, right, with the best coding practices. So with this, since we had coding practices in our last statement, right, which I just said, we will dive into Python coding starting tomorrow. And this is a fantastic programming language that I want you all to learn and become very familiar with. As always, if you have any questions, feel free to put them in the chat, and I will see you tomorrow. Stay tuned.